As you know, one of the unique properties of gases is that the particles that comprise a gas are in rapid random motion. The kinetic molecular theory of gases attempts to explain the ideal gas law in terms of how gas particles are moving. The kinetic molecular theory of gases was built up assuming 5 main ideas. The first is that the volume of gas particles is negligible compared to that of the container. That is, there's so much space between the gas particles that their volume is not worth considering when we're performing the mathematics of the kinetic molecular theory of gases. It is also assumed that gas molecules move in rapid random motion. That is, they're not influenced by any outside force, they're just moving around randomly. It's assumed that the only factor that affects the kinetic energy of a gas is its temperature, and in particular, as the temperature increases, the kinetic energy of the gas will increase as well, and if the temperature decreases, the kinetic energy of the gas will decrease. It's assumed that all collisions are elastic, that is, that energy is not lost when particles collide with either each other or the container walls. The kinetic energy of the system is constant if this is the case. It's kind of like the gas particles are the world's best bouncy rubber ball. There's never any loss of energy during collisions. And the final point is it's assumed that there are no forces between gas particles. The gas particles neither attract nor repel one another. So, according to the kinetic molecular theory, at a given temperature, the kinetic energy for a gas will be constant. However, it should be recognized that there will be a distribution of speeds of the gas particles. Some gas particles will be going very fast, others will be going quite slow. The most likely speed, the most probable speed, will be at the peak of our curve. And an important speed for us is what we call the root mean square speed, which is just a little bit on the high side of the average or most probable speed. And the reason why that's important is it turns out that that's relatively easy to calculate. The root mean squared speed is the speed of a gas particle that has average kinetic energy. And you might recall that the kinetic energy of a particle is given by 1/2 mv squared, or in this case it would be 1/2 m root mean squared speed squared. Now, as the kinetic energy of our system depends only on the temperature, this turns out when we do the math is equal to 3 on 2 RT, where R is the ideal gas constant and T is the temperature in Kelvin. So if we combine these two relationships, we can come up with a simple equation for the root mean squared speed of our gas particle. And so the root mean squared speed is equal to the square root of 3RT on M. R is the ideal gas constant, T is the temperature in Kelvin, and M, uppercase M, is the molar mass. Now, there are some interesting things. Because of the way that energy is defined in the SI system, we need to make sure that our molar mass in this equation is given in kilograms per mole. That is, you need to take the value from the periodic table and divide by 1,000. And we need to be mindful to use the ideal gas constant with the appropriate units and value. So we want to be using the 8.314 kilograms meters squared per second squared per mole per Kelvin units here. So just remember, R has to be 8.314 and your molar mass needs to be given in kilograms per mole in order for this formula to work properly. So now it's kind of fun. If we know the identity of our gas, we know its molar mass, and we know their temperature, we can calculate the speed. So let's have a look at this. It says calculate the root mean square speed of neon atoms at the temperature at which their average kinetic energy is 5.18 kilojoules per mole. So first of all, we need to go to the periodic table and find the mass of 1 mole of neon atoms, and then divide that by 1,000 to get that mass in kilograms. Now, we know that the average kinetic energy is given by 1/2 m root mean squared speed squared. So, if we rearrange that formula, we can solve for the root mean square speed. So going ahead and doing that, obviously 2 is just 2. This is our average kinetic energy, but note that I times it by 1,000 to take into account the kilojoules there. I also expressed it in the base units so we could see how the units cancel. And then we have to divide that by the molar mass expressed in kilograms. There it is there. And of course, take the square root of it all. Now, turns out that at the temperature at which the average kinetic energy of the neon atoms is 5.18 kilojoules per mole, the root mean squared speed is almost 700 meters per second. And normally these root mean squared speeds at ordinary temperatures are several hundred meters per second. This one's a little easier. It just asks us to calculate the root mean squared speed of O2 at 298 K, which is a little over room temperature. So we're just going to use this little formula here. The root mean squared speed is equal to the square root of 3RT on the molar mass. So we know the molar mass of O2. We just multiply the mass of an oxygen atom by 2, but we need to divide by 1,000 to convert it to kilograms per mole. Our temperature is already given to us in Kelvin, and we just got to remember to use the 8.314 value for R, not the 0.0821 value. So once we've got all of our variables organized, we're just going to put it into our equation. 3 times R times T divided by the molar mass in kilograms per mole, and then take the square root of everything. And sure enough, it ends up being 482 meters per second. And that's kind of reasonable because we're expecting these speeds to be of the order of a few hundred meters per second. So let's take a look at the formula for root mean squared speed. So the root mean squared speed formula is telling us that as the temperature goes up, that the speed will go up. It's also telling us that as the molar mass goes up, if everything else is constant, then the speed will go down. That is, the root mean square speed is inversely proportional to the square root of the molar mass, but it is directly proportional to the square root of the temperature. So, what this is saying to us is that heavier gases on average will be moving at lower speeds. And what we find is that heavier gases will have a lower most probable speed, but they will also have a narrower distribution of speeds at a given temperature. And so this is looking at the noble gases, which increase in mass as we go down the group, and you can see that an exact phenomena is occurring as we get to heavier gases at a given temperature. The distribution of speeds becomes narrower and slower. Now, If we have the same gas, but we increase the temperature, we see the opposite effect. What happens is that the average or most probable speed will increase and the distribution of speeds will broaden. So here's an example problem where you're asked to think about labeling a series of curves. It says the following curves depict the speed distributions of samples of 1 mole of gas at 0, 1000, and 2000 degrees Celsius. Which curve belongs to which sample? So lower temperature means slower speeds and narrower distribution. So that's going to be my lowest temperature. And then higher temperatures mean high average speed and a broader distribution of speed. So this is going to be my highest temperature. So it's pretty obvious that the orange one is 0 degrees Celsius, the green one is 1000 degrees Celsius, and the blue one is 2000 degrees Celsius. Okay, so that concludes the video on the kinetic molecular theory of gases. I hope you found it helpful.